Professor Joule, I think we can start. Thank you.
Ren, thank you very much. Okay, good afternoon, everybody. Good evening, good morning also. So welcome to this Princeton Combustion Summer School on plasma-assisted combustion. So yesterday that we started to discuss about that laser diagnostic method for plasma-assisted combustion. And we introduced that the Thomson scattering to measure electron number density, electron temperature, and we also introduced that called E-phase second harmonics to measure that electrical field. And then we talked about using femtosecond cores to measure a non-equilibrium temperature distribution and some of the key species. And today we continue to introduce some conventional techniques using a TALIF, two-photon laser-induced fluorescence. So TALIF is a effective method to measure that atomic species. For example, you have oxygen, hydrogen atoms, and you have nitrogen atoms in the plasma. And you can use in TALIF to measure qualitatively or even quantitatively with calibration about this atomic species concentration. For example, to measure oxygen atom, and you can excite that with a UV laser at 225.6 nanometers with a strong laser power. You generate two photon laser absorption to electronically excited state. And this electronic excited state of atomic oxygen then relax to the lower excited state and emit that 844 nanometers of fluorescence. So you can use this fluorescence intensity with a calibration to measure the number density of atomic oxygen. So the TALIF atomic oxygen has been studied for a long time. You can see if the literature in the bottom, and we try to, the TALIF is a nonlinear method that because it involves two photon laser-induced fluorescence. So therefore the TALIF signal is that the proportional to the square of laser intensity. So try to give you an example that what TALIF has been used to measure species like O and H and N and CO and NH. So the detection limit is about to go to very low. It's about 10 to the 11 to 10 to the 12 cubic centimeters. So here showing you a laser setup, and this is the laser setup at the Princeton University. And you can, using, for example, so n-dodecane laser, and to generate that laser pulses, and you can mix it with that using a nonlinear mixing to generate the wavelengths. For example, you wanted, and then you can collect that the signal by using a PMT, and then measuring that the signal of that the targeted atoms. For example, nitrogen atoms. And you need to calibrate this with, for example, if we measure nitrogen atoms, will be two photon at 206. And you need to calibrate it with a krypton and at the similar laser energy and with similar emissions. So you check that the signal ratio of a atomic nitrogen and krypton, and this A the coefficient, so that is the fluorescence a quantum yield. And these are the cross sections of two photon laser induced fluorescence. And these are the laser energy at a different frequency for a nitrogen atom, krypton, and this is the number density of krypton, you know. So using this krypton number density to calibrate what is that the number density of N atom and, for example, O atom. So this is the example that the experiment we have done, and in 2011, 10 years ago, detected that the oxygen in a plasma in a countable flame. You can see that the plasma generates very strong atomic oxygen and in a countable flow flame, and allow you to detect that the concentration using TALIF method. So you can also using femtosecond laser, and we can use using a picosecond laser, femtosecond laser, or nanosecond laser. So here is that if you're using a femtosecond laser, the laser energy is intensity is much stronger. So you can actually do 2D imaging of key radicals. This is that the atomic oxygen measurement done by Dr. Schmidt. So measuring that, this is that the discharge and atmospheric plasma jet. So you can measure the two-dimensional distribution of atomic oxygen distribution. So this gives you a qualitative and quantitative understanding about how much active species, atoms, is generated in plasma. And by using the combination of this process, for example, you can using cavity rundown, you can using TALIF, you can using E-fish, and also Thomson scattering. You can quantify the plasma properties and the plasma chemistry. So here example we talked to you before is that the Professor Christophe Laux in France, and he measured that the plasma discharge in nanosecond discharge and air at 1,000 Kelvin atmospheric pressure with 10 nanosecond pulses with a different voltage and frequency. And he tried to measure that atomic oxygen by TALIF, and he measured that nitrogen and nitrogen excited species by cavity rundown spectroscopy and emission spectroscopy. And the electron number density at that time, he was using hydrogen H beta. So stock broadening, we talked yesterday, and they're using that stock broadening. So this can only measure when the electron number density is very high, above that 10 to the 14th or 15th per cubic centimeters. So here the result, I don't need to say, and I already showed this figure many times because it's so important to understand that the plasma dynamics. So you have a 10 nanosecond pulsar, and right after the plasma, you generate excitation of B and C state of nitrogen. And this is measured by emission spectroscopy. And the A is measured by the cavity rundown, CDRS. So you can see that the right after plasma, you generate the excited nitrogen, and this excited nitrogen decay, and then followed by that the rising atomic oxygen. So this gives you a very rich dynamics and the time scales of different plasma. So let's see what is the summarization from this experiment. The summary from this experiment basically say that you have two-step mechanism for atomic oxygen production. The first step is the electron impact with nitrogen, generate excited nitrogen. And then the second step is that the excited nitrogen reacts with oxygen, and then the dissociated oxygen into atomic oxygen, and with generate heat. So this again generate a fast heating. And then you can plot in this image. Okay, the electrons collide with nitrogen, and you generate excited states of nitrogen, and then excited state of nitrogen collide with oxygen. You generate this two atomic oxygens plus energy. So in addition, that electron impact with oxygen itself also generate oxygen and depend on the energy. So these active species generation and help that the oxidation or ignition and in plasma assisted chemical processing. So that allow you to enhance combustion and chemical processing. And also that the fast heating from that the plasma can generate a thermal effect, enhance flame stabilization as well. Similarly at Ohio State, and yes, about Dr. Woody right now is the University of Alabama, and worked with Walter Lampert, and then he measured that the atomic oxygen production by using TALIF and using nanosecond lasers. So here it's showing you that the distribution, the time sequence of that atomic oxygen production. You can see in the air, you can generate a considerable amount of atomic oxygen, 10 to minus 5. And but with fuel addition, your atomic oxygen dramatically reduced, and in a time scale about 0.1 millisecond. So this clearly indicating that when atomic oxygen is generated in a fuel mixture, and that atomic oxygen is removed, and it is participating in the reaction to oxide the fuel, and then is quenched. So you can see this TALIF give you very sensitive diagnostics and to measure the time dependence of atomic oxygen, and also give you that the understanding about that the role of atomic oxygen in air and in the fuel, they play different chemistry. And again, I try to repeat that the measurement of singlet oxygen, oxygen molecules, and asinglet states, and you can use in ICOS cavity, just like a cavity rundown. So you can measure this excited state and at a visible range. So you can amplify it. You can see that this is the ground state, and this is that the oxygen A singular delta, and this is at the B sigma, and this is very close to 1 electron volt. This generates a lot in terms of DBD plasmas and gliding arcs. So we shall talk to you yesterday that by using a ICOS cavity, the off-axis ICOS cavity, and then you can using that the almost visible light. You can see that is 663 wave number, and to using that the absorption to measure quantitatively measure that the single delta about the oxygen molecules. The sensitivity probably about 50 ppm sensitivity, which is enough for you to quantify that the singular oxygen productions in DBD. So this is at the absorption frequency, and this is at the with and without a singular oxygen. You can see that the absorption curves. So another important thing is that in plasma is try to measure the HO2 formations and also OH formation, because in low temperature plasma, and that the radical production of H and O eventually quickly become into either OH or and become HO2. So a low temperature HO2 is quite stable. So very important to measure HO2. But HO2, water, and OH, they share a similar absorption band at the infrared. It's very difficult to measure it just HO2 or just OH, and in a infrared laser absorption. And there are previously there are people and developing, for example, using laser reaction of HO2 with NO, convert that HO2 into OH to NO2, and then indirectly measure that the OH using laser absorption or planar laser induced fluorescence. Today we try to introduce you that the method we developed here at Princeton through collaboration with Professor Wasaki, using mid-infrared Faraday rotational spectroscopy. The Faraday rotational spectroscopy is that you basically using the properties of paramagnetic properties of HO2 and OH, because they are paramagnetic. So if they are paramagnetic, so therefore they are very sensitive to that the magnetic field of a photon. So if you have a laser beam coming in and you polarized with a certain angle, so the light is polarized with one plane. And if this laser is going through with HO2 and OH in a mixture, and when you apply a magnetic field, so this magnetic field will causing that the broadening of this energy band of paramagnetic molecules. For example, at HO2, if without magnetic field, and you basically, this is the ground state, and this is at the upper state. So the energy is very close, and you don't have to, you cannot distinguish even. But if you put a magnetic field and this electron spin orbitals, the electron spin and will change their direction, following the direction of magnetic field. So therefore, this energy will be splitting. If you, the quantum numbers will be 2j plus 1. So 2j plus 1 is a 2 multiplied by a 1/2. So that was 3 plus 1 will be 4. So this energy will be split into 4 energy and with different spin directions. And similarly, the upper energy will also be split into 4 energies. So this splitting allow you to sensitively detect that the HO2, because only HO2, they will split at this energy. So, but once that the energy is splitting, and then this absorption is depending on that the polarization of that of the light. When the laser is coming in, polarizing, you can have a left rotating, you can have a right hand side rotation, polarization. So if you're looking at that absorption, you can say the right hand side polarized light, and they absorb between the red, the lines indicating the red. And your left hand and the polarized light will be absorbed by this the green arrows. So therefore, that by using right and the left absorption, polarized photons, you can tell that the concentration of HO2. If because the absorption coefficient on this right-hand side circulation or left-hand side circulation polarized lights, they have different absorption coefficient. So therefore, initially you have a polarization in this angle. After you pass this HO2, because that's the right and the left, they absorb in different amount. And then you can see the right absorb more and then the left absorb less. So therefore, in the output photons will have a different polarization angle. So this polarization angle is proportional to the concentration of HO2. So therefore, that the concentration of HO2 will be proportionally to that what is that the polarization angle change. And initially it's here and output is there. That kind of angle change and will determine that how much is that the HO2. So by using this, you can see that we can detect that the HO2 and in a flow reactor and up down to 1 ppm level per frequency. This is a modulation. So we can measure OH with 3 sigma at 20 parts per billion level and the accuracy. So this allow you, the Faraday rotational spectroscopy allow you to do a sensitive diagnostics of HO2 and OH and in low temperature plasma. And it's very useful. I'll show you that how that these will be applied to in plasma chemistry. The other method like OH measurement, it can also using ordinary laser-induced fluorescence, like a single photon laser-induced fluorescence, like a TALIF. So this is an experiment and in a plasma reactor and conducted at 500 Kelvin and 100 Torr with hydrogen air and ethylene air. So you can measure that how much OH concentration as a function of time with a different pulses and or with different equivalence ratio. So this give you a quantitative or qualitative, depending on your calibration about the OH concentration. It's very standard and in combustion diagnostics. And for low temperature, for example, cool flames, and your OH concentration is very low. It's probably below 10 ppm. And at 10 ppm level, the TALIF also give you very sensitive diagnostics to measure that the OH concentration in a cool flames and in plasma. So what I try to say that plasma, they couple with combustion chemistry at high, intermediate, and low temperature by producing these active species, O and O1D, OH, and vibrational state and singular oxygen. If you can detect all these species and electrons as well, and in plasma, and you can considerably enhance understanding about the plasma chemistry. As you can see that we know we can measure electrons, electron temperature, number density, and electrical field. We are able to measure atomic oxygen, atomic H. We are able to measure excited nitrogen, and using cavity wind down or using emission spectroscopy, we are able to measure HO2, and we also are able to measure nitrogen vibration by using picosecond cores or using tunable diode laser at infrared. And also we can measure ozone, can measure singular oxygen. So all these techniques developed can be used to quantify these kind of elementary reactions. It's a very powerful tool. So therefore, as I said yesterday, that what we really need to understand for combustion, we pretty much understand the chemistry reasonably well. And you can go down to make it understand better, but we are almost there. But for plasma, that the chemistry is not well understood. And interaction between plasma with flames, particularly low temperature flames, really is poorly understood. I think that the research focus should be focused in this kind of a yellow region and this green region to understand plasma assisted combustion and chemical conversion. All right, these are the lists that the reactions we really don't know quantitatively, and particularly that how, for example, O1D reaction with large alkanes or oxygenated fuels, vibrational oxygen reaction with this, how do they RO2 vibration? Do we know the reaction rate? So it's not very clear at all. So we're trying to share you one application that the diagnostics developed to measure elementary reaction rate of plasma chemistry. For example, O1D, O singular delta, excited atomic oxygen reaction with fuel is a very, very important reaction because this O reaction with fuel is a multi-channel, you can see, and involving direct insertion of O into CH bond and CO bond. So therefore, this O reaction with, for example, with alcohol is not just to attract the H, but also they can insert that O into the CO bond and into that the CH bond. They form different channels. So then the question that what is that reaction rate and what is that the branching ratio of different channels? So this has been a puzzle for quite some time, and in terms of O&D reaction with alcohol molecules. So by using that the Faraday Rotational Spectroscopy and integrating with a photolysis reactor, so we're using that the UV to photolyze that the ozone to generate O&D, and we flow that ethanol into this reactor, and we're using Faraday rotation to measure OH, HO2, and also using laser absorption to measure other species. So this is experimental setup. This is that the photolysis reactor. This is a magnetic field generated at the Faraday rotational spectroscopy, and this is a UV laser and to photolyze the ozone. And we on both sides of this reactor we have this infrared mirrors to allow us to do direct laser absorption spectroscopy, and also that they're using this Faraday rotation to measure OH. And this is that the experimental result. Try to show you that using a laser absorption FRS, we can measure OH as a function of time, and after that the photolysis. We can also measure, as you can see, that we can measure that HO2 as a function of time as well. And by feeding this time sequence of OH and HO2 and other species of, we can determine that the overall reaction rate of this O1D reaction with ethanol and also measure that the branching ratios of each reaction. For example, O1D reaction with ethanol to produce OH with ethanol radicals. This reaction channel is about 44%. And then that the oxygen insertion reactions that, for example, you generate a methoxy with a methanol. So this is a very reactive reaction channel. They occupy 42%. And these other two channels, they probably about 14%. So understanding this branching ratio and reaction rate is very important to develop a chemical kinetic mechanism using. And this is a figure I showed you before. That is the work done by Professor Richieder at Penn State. And he using a flow reactor, high pressure flow reactor with plasma discharge, measure that the species distribution with and with plasma. This is that without plasma, this is with plasma. You can see that the plasma generate a lot. He using a GC and to measure the species concentration, which also give good information about the plasma-assisted low temperature fuel oxidation. So this is that collaboration between Niels Hansen at the Sandia National Lab with us, and measuring that the kinetics of ozone reactions with methyl hexanonate H. And this is that the biodiesel molecules and using molecular beam with a flow reactor. And you can see that with ozone, so you can see a extreme low temperature, ELTC, extreme low temperature oxidation of the fuel around that, even below 500 Kelvin. And without the dashed line showing that without plasma, you only can see low temperature oxidation above 550 Kelvin. So therefore, and plasma give you a new reaction regime at the extreme low temperature due to that the atomic oxygen formation from ozone dissociation. And you can measure all other species using synchrotron photoionization, synchrotron spectroscopy. You can see what are the intermediate species measured below 500 Kelvin. You can see a lot of hydrogen peroxide. You can see that the diketones. You can also see that some kind of acid formations and many other species using that photoionization spectroscopy. So, and then I talked to you yesterday that you can see that plasma generate a NO, and this NO has a different impact in terms of n-dodecane oxidation. They can delay that the n-dodecane oxidation at low temperature, but accelerate at intermediate temperature, like 700 Kelvin to 1000 Kelvin. So sensitive diagnostics using lasers, molecular beam spectroscopy, and the GC and other things can dramatically enhance the understanding of plasma chemistry. All right, so next thing we'll try to show you that using multi-species diagnostics. And just like those and used by Professor Ron Hansen at Stanford in a shock tube, try to detect the multi-species as a function of time so that it can develop a chemical kinetic mechanism. So here at the Princeton, we developed this kind of a flow reactor with a plate-to-plate, plane-to-plane, a direct barrier discharge, DBD discharge. You have a flow in this direction. The plasma discharge is from the top to the bottom. And you build a Harrier cell inside this, between the wall of this flow reactor. And that allow you to do a laser absorption or a multi-pass laser absorption using different kind of lasers. Here we have this Q cells, we have this DFB lasers, we have a photodiode lasers allow us to measure different species as a function of time. This is the experimental setup, and you can see this is the quantum cascade lasers, and these are the plasma reactors, electrode, and the budding electrode. And this is housed to avoid that the moisture and in that, and also housing that the electromagnetic noise from the plasma generator. So this is that the plasma discharge of ethylene oxidation with in oxygen with the plasma. And this is a C, you can see ICCD image to show you that the plasma discharge is fairly uniform at 60 tall with a 6 kilovolt and 10 nanosecond discharge. So we use this diagnostic method to do, for example, n-dodecane. We study the pyrolysis. We study the oxidation by keeping the same fuel concentrations, replacing nitrogen by oxygen at a 30 tol as a flow rate about half meter per second. We can using GC to measure these species. We can using FRS and Faraday rotation to measure NO. We're using a TDLS to measure fuel and all intermediate species. And so here I'll try to show you that we can develop a kinetic model for n-dodecane by considering that the plasma chemistry with excited oxygen and oxygen atoms, excited nitrogen and ions of nitrogen and oxygen, and coupled with a NOx chemistry. And the key issue is that the data is missing for cross-section areas of excited species with few molecules. So we have to, using a pyrolysis experiment to fit that cross-section areas of these reactions, and before we conduct the oxidation reactions. So as you can see, this is a voltage curve, this is a modeled, and this is measured and modeled, and this is the temperature, and we're using the measured temperature as the input of that modeling, because that the reactor has different heat losses. So it's important to using the measured temperature and to model that the species concentration. So you can see this is the NO measurement using FRS. I talked yesterday that in the air you have a lot of NOx production by putting fuel, and your NOx basically is dramatically reduced by converting that the NO reaction and with that alkyl peroxy radicals that form to NO2. And so we can compare that the few molecules as a function of time. This is the plasma discharge, and we can compare that the in situ measurement of methane acetylene as a function of time, and this is at the experimental measurement. This is at model prediction, and we can also measure that for example, water formaldehyde. This is at the model prediction with the experiment. This is at the formaldehyde model prediction with experiment. There are some discrepancy for formaldehyde, but in overall, that the model predicts reasonably well in terms of a small species. And you can also compare with that a stable species by using GC. You can measure a lot of species and small hydrocarbons, and you can compare the model and with that the species. Remember, this agreement extremely well. It is because we fit this experimental data to obtain that the cross-section areas of excited states reaction with fuel. So now we compare with oxidation case using the same cross-section area. You can see that we compare the predicted that the formaldehyde, CO, and hydrogen, and they agree reasonably well for that the major species. For minor species, there's some discrepancy, and this probably is because that the electron impact reactions. So we did not calibrate that with the electron impact reaction. If you using this data to further calibrate electron impact reactions, the experiment will agree much better with that the prediction. So this gives you a highlight of one example that using this multi-species diagnostics, you can able to develop a qualitatively experimentally validated kinetic models for plasma assisted combustion of a transportation fuels. Unfortunately, that as I said before, there are available, for example, cross-section areas for small species. But anything larger than C5s, you can see is not here. So we have to using experimental data to calibrate that the reaction rate and cross-section areas. And non-equilibrium kinetics, as I said before, for example, in low temperature combustion, everybody is understand that these are free radicals reaction with oxygen, they form alkyl peroxide, proxy radicals, then they become QOH, and these are very important channel and for chain branching. However, if that the few radicals or the oxygen radicals are vibrationally or electronically excited, and how does this reaction channel will change? This is an open question, and nobody really understand what is that how much the reaction channel will change with this electronic and vibrational excitation, and how to measure the vibrational excitation of few radicals and in the experiment, and it's very challenging issues as well. I try to give you some kind of summary, and over the last 5 to 10 years, the significant progress in terms of in situ laser diagnostic method for electrical field, electron density, electron temperature, excited species have been developed. And this method has been used to quantify atomic oxygen, O singlet, O2 singlet, nitrogen excited species, HO2. And this method has been used to measure elementary reaction rate and to develop chemical kinetic models and for plasma-assisted fuel oxidation. So I expect that in the next few years, more in situ diagnostic method will be developed and applied in these areas. And I would like to stop here and to finish that the lecture of laser diagnostic. I would like to take any questions. Any question here?
No, there's still no questions yet.
No question?
Yes.
Oh, great. So, all right. So let me move to the next talk. Also integration about, so next talk, let me switch that the talk a little bit. So let's talk that the plasma instability, that's the lecture 8 first, before we get to the plasma modeling. So if you have any question, you can ask me. So let me share screen. Can I continue?
Yes, we can see that.
So let me continue that in the next probably 30 to 40 minutes, I try to share you that a new type of instability happening in plasma-assisted combustion and chemical conversion. In combustion, that you have hydrodynamic instability, you have thermal diffusion instability, and you have acoustic instabilities that are driven by a density gradient, driven by a preferential diffusion, or driven by acoustic wave interactions. And in plasma, there are many different instabilities, but few of them, they involved with chemical reactions in combustion or chemical conversion. So I'd like to show you, you can see from this video that initially you have very uniform discharge. And after a function of time, you can see a lot of contraction is happening. So this is that the plasma discharge in a fuel mixture. So why do we have to answer this question? And this is a try to disable hiding. So one day I was, probably in 2019, I was on a flight to an international conference. And then I read this news. This is that is a flying rocket of Russia on May 27, 2019. So here is the rocket. The rocket is rising. They're struck by this lightning. And you can see the lightning connect to the head of this rocket. And then the black smoke is probably that the exhaust gas from the rocket. You can see the lightning just traveling, and in the tail gas region from the rocket. And I try to ask myself, why does that lightning and love that the exhaust gas from a rocket, right? So if you think about it, and the exhaust gas of rocket is actually, is unburned hydrocarbons, because kerosene rockets, most of the rockets run fuel rich. So equivalence ratio is 2 or 3. So therefore, the exhaust gas is actually just like a CO and hydrogen, probably methane, and this are unburned hydrocarbons. And then the question is, why does this plasma like hydrocarbons, right? So that is the question I was asking. And then I started to ask my student to do the experiment, whether that there is a instability triggered by chemical reactions of hydrocarbons to accelerate that a contraction of plasma to form this lightening. And as you can see, this is a figure I showed you in the first day on Monday, that recently there's people observe that maybe in Australia, that they observe that after you have a fire, and this fire exhausts the unburned hydrocarbons, attract a lot of lightnings, and they publish in Science. So sometimes I feel like that the paper published in Science is just like a superficial, just like an observation, and really not much of a science. It's just like that observation about the phenomenon. But really that the science is here. Why does that the plasma become unstable when they see hydrocarbons, right? So this motivated me to ask the question. And then for chemical processing and in industry, and you don't want plasma instability. You want plasma to be very stable and uniform so that it can process a fuel in a large volume. So then the question that it becomes very challenging when you try to process that chemicals at atmospheric pressure, and the plasma is always becomes an arc. And the question that how do we control it? If you want to control it, and you have to understand why does plasma want to become unstable when they see a hydrocarbons or fuels. So this is a big question. And also the same thing in advanced engines, as this like Mazda engines, they're using plasma to initiate that ignition of HCCI. And you don't want the plasma to contract much. You want the plasma to be bigger volume. So the question that what is the mechanism? So all these things try trigger to me to answer one question. Why does plasma become unstable when they see hydrocarbons? So what is the mechanism? So if you try to learn what is the mechanism, and you try to looking at the textbook of plasma, if you're looking at the textbook of plasma, they always say, okay, you have a vacuum tube, you have a cathode, you have an anode, they give you a glow discharge, very volumetric. But if you increase the pressure, and this plasma become contracted, and they are unstable as a volumetric discharge. And at the same time, when you do experiment, this early experiment around 1970s or 2000, you can see that if you put a plasma discharge in a helium or in argon, you can see the plasma has two forms: is a diffuse discharge, very uniform, and is a contract. This contraction is because there is instability, and the instability makes this volumetric discharge become a thin arc. So what is the mechanism? Well, this mechanism has been studied by many people. They say typically this kind of electrical field and a current curve. So if you increase, for example, if you add a lower current and your plasma is uniform like this, the electrical field is very large. If you increase that current to a critical point, the plasma will contract, become like this. And then the current, and then the plasma electrical field is very weak, and the voltage will drop dramatically. And you can see if you reduce it, they continue to be contracted until that the current is so small, and they go back to the uniform discharge. So this looks like exactly like what? Like combustion S-curve. This is like a flame extinction. This is like an ignition or something like that. The mechanism of this is quite simple. And if you're looking at the plasma textbook, it will tell you that it's because the electron number density is proportional to the Joule heating about the current. As a large current, you have more Joule heating. You have more Joule heating, you got more temperature. You have more temperature, temperature is high, and the number density will decrease. The mean free path will increase. When the mean free path is increasing, your reduced electric field, electric field divided by the number density will increase. This will raise the electron temperature, will increase the plasma ionization, and drive the instability positively going. The magnetic plasma instability to happen like this. So this is pretty much called thermal Joule heating. Instability is controlled by Joule heating. And then the question to ask you is that, what if that I put that the methane and or some kind of unburned hydrocarbons? Does that the combustion chemistry will affect this instability? Yes or no? And so with that, and so I try to explain this. This is that the experiment we done in the lab to see that the fuel and air mixture, they have some kind of instability. This is the rocket flying the lightning like to track it. And so this is that the chemistry we just discussed it before. This is the combustion chemistry, this is the plasma chemistry. They couple together. And the question is that, how does these affect the instability? All right. With that question, I submitted a proposal to National Science Foundation 2 years ago, and then try to answer this question. And then fortunately that the proposal was reviewed well and funded. So in plasma society, we know that the thermal instability, this is Joule heating instability. We know that, I just showed you before. So what I try to propose is that in a combustion, plasma cyclic combustion, you have a new instability. They call plasma chemistry instability. This instability is due to that the plasma induced chemical reaction, they are going to change your electron number density and make it high, make it lower, and they are going to generate a heat release. They are going to generate, endothermic process due to that the pyrolysis. They are going to generate electron attachment to the water formation in combustion. And how does this chemistry is going to impact instability? And how does that explain this guy? So that is something, and we want you to study. So we'll try to tell you 3 things, and experimental demonstration about plasma chemical instability, and then a theoretical analysis about the instability criteria, and then computational study about that thermochemical instability. So let's go to the first one, experiment. So we now have a lot of diagnostic methods. We can measure electric field, we can measure plasma temperature, number density. And we want to understand that in this kind of plasma reactor, and 50 tall room temperature, and with nanosecond discharge, 12 nanosecond, for example, 30 kilohertz, with the mixture, let's say with and without fuel and in oxygen, and see how that instability will be different. So we can measure electrical field by using EFISH. I talked about yesterday, we don't want to repeat again, and see how does electrical field change with that instability. So I show you the figure, you can see this is that the image about the nanosecond discharge in a methane, oxygen, and argon mixture at the pulse time at 25, 100, and 150. You can see initially that is very uniform. As you increase the pulse time, and then the plasma becomes more unstable to form this kind of a streamer. All right. So is that due to combustion, or is just because it's argon and oxygen? So then we try to say, okay, we do a high-speed imaging. So without combustion, we just that we do a plasma discharge with a oxygen plus argon. You can see that the plasma is very uniform. So at the same time, we keep that the oxygen is the same, and we replace that argon by using 6.6% of methane. You can see that the plasma instability is developing. So this clearly shows that that the plasma-assisted combustion is going to enhance the plasma instability. And this partially explains that why does that the rockets, they like, and the forest fire, they like to catch the lightning. So if this is correct, then how do we measure that the electric field when instability happens? So first of all, we do using applied electric field, and we calibrate the E-fish, make sure what we measured is equal to what we apply. So after this calibration, and you can start to see that the make a single shot. This is at the one-dimensional. This is at a photon count. You can see this is what happens at different shots. When instability happens, that you can see a spike. It's a very small spike, a very small spike. This spike is very small, is only at the micron size. So that means this spike showing you that there is a plasma instability is happening at near the electrode at a very high electric field, a very small scale. So indicating that the plasma instability is happening at a very probably a at the micron length scale. So if you're looking at it, you see, if you're looking at the time-dependent measurement, you can see the spikes of electric field. And so let me play again. So you can see the spike is happening. Well, it's not going. Anyway, why it's not going, I don't know. So this is clear that if you say you can use in pentane, the pentane has a low temperature chemistry, and you can see the instability is very clear if you replace the methane by using pentane. If you remove the pentane, the fuel, just leave it with argon and oxygen at the same concentration, and you don't have any instability. So all this experiment basically suggests that that if there is some kind of new instability mechanism that is going to be enhanced by plasma-assisted combustion. And now we try to, before I take a break, okay, so let me take a quick break and then come back. So all right, so right now it's 3:30. So so is there any questions?
No, there isn't now.
No question?
No questions yet.
Okay, I think that the audience is very, very polite or very, very quiet. All right, so let's come back in 10 minutes. So right now is 3:35. Can we come back at 3:35?
Yes.
All right.
We are ready, Professor.
All right. So let us continue. All right. So as you can see that in experiment, we can demonstrate that by adding fuel into air, we can see that the plasma instability is enhanced. And the next thing that we try to understand that how do we understand this by doing a very simple and detailed chemistry analysis. So my graduate student and Han Tao and conducted this analytical studies. You can write down that the governing equation that the electron number density change will be proportional to ionization rate, electron attachment, convection, electron detachment, and then electron ion recombination and the diffusion. And you can also write down that the neutral molecules is because of the attachment, the diffusion, and the recombination, detachment, and then diffusion and ion-ion recombination. And you can write down that the temperature change due to plasma Joule heating, due to the convective heat loss, due to combustion heat release, due to vibrational rotational relaxation, and I don't know why there's one negative sign here, but anyway, so due to that, the diffusion heat losses should be 1. And then if you do that, and my slide is frozen somehow. Let me stop it and share it again. Can I move it? So I cannot move it. Okay, so sorry for that. So let's continue. So as you can see that we can write down that the governing equations for a simplified model to understand the dynamics of plasma instability. To do that, we try to introduce a linear perturbation. We try to perturb the electric field and reduce the electric field as a function of temperature and as a function of electric field. And because the reduced electric field is a function of number density, which is a function of temperature. We can write down the temperature is perturbed by some kind of wave function. And at the same time, that electric field will be perturbed in the same way. We substitute this perturbation using temperature and electric field back to the governing equation. And then this lambda is a complex number. So we try to understand that if lambda, the real part of lambda is, let's say, is positive, and then this perturbation is unstable. And if the real part is negative, that the system is stable. So you can substitute this into the governing equation and analyze that how that the real part of that the eigenvalue is going to change with time. For example, in energy equation, and the perturbed equation can be written like this: the ionization rate as a function about the electric field will be a function of convection and combustion heat release. So, and then you can plot that the real value of the wave as a function of current. This black line basically says that if I don't have any kind of combustion heat release, and your plasma instability will be happening around 9.5 milliampere. But if you have a combustion heat release is negative, that means if your system is endothermic, and then you have the plasma become stable even at 10.5 milliampere. If on the other side, if you have combustion heat release, that the QC is larger than 0, then your plasma stability will reduce to 8 milliampere. So this figure basically clearly sees that the heat release from combustion is going to destabilize the plasma and triggering that the plasma to be unstable just from this eigenvalue analysis. And next thing we try to say, what is the vibrational rotational relaxation? So if that vibrational state, that the vibration rotation translational relaxation time, let's say is very, very short. Very, very short means that the vibrational energy will be quickly transferred to the translational energy, and they generate heating. In that case, you can see your plasma becomes more unstable. If that the vibrational state that can have a long time scale, take a long time for vibration energy to transfer to translational, and in that case, that your instability is decayed. So this figure basically is showing that the vibrational state also provides a critical role to stabilize that the instability, and if you can trigger the vibrational states and for long time relaxation. And if you plot that the electrical field as a function of current, and you can, the solution will be like this curve, okay? At this point, you will see that the eigenvalue on the right is become unstable. Positive, the eigenvalue on the left become unstable. That means at a low current, and this the solution will be stable, and high current will be unstable. So these are two different branches. So at the stability point, you have derivative of electricity to the current, the dE di, they all equal to 0. So this is at the boundary of stability. All right, so we can try to say that how can we derive an analytical equation to express that instability? And if you're looking at, if we develop that the cross-section areas and then electrical field, d log sigma, the conductivity is actually the current. The current sensitivity to that to the electrical field, it can be analytically derived as this function. It's too long for you to understand. Let me walk you one by one. The first term basically says that this is the delta prime is showing that there is an ionization rate. So therefore, the instability is going to be controlled by a plasma ionization rate. And the second thing that is showing you that the mole fraction or mass fraction change due to that the plasma kinetics. So the plasma kinetics basically change your ionization rate, and that changes your composition. This composition change also affects your instability. So this left term is pretty much the plasma chemistry. And the right-hand side term here is that showing this is the heat losses, that the time scales of cooling and affecting your instability. And this basically showing that vibrational relaxation, and from high level to low level, they also affect the instability. So this term basically showing the vibrational translational relaxation, they're going to affect the instability. And this basically showing the combustion heat release that changes the instability. And this whole product -2 has to be equal to 0. So therefore, this one is a negative sign here. The product of these two terms, if it is bigger than 2, the plasma will be stable. If it's less than 2, if it is less than, what I say that is less than -1. If it's less than -1 or -2, it should be less than -2. If less than -2, they will be unstable. Negative, so means that the heat loss negative means this term will have to be positive. That means the relaxation has to be positive very fast. If this one is a relaxation, if the VT relaxation is big, then plasma become unstable. If the combustion heat release is large, it becomes unstable. If that is the ionization rate, for example, is very sensitive to electron number density, is unstable. So this basically that the stability equation tell you that the physics, not only that the plasma and Joule heating, here's Joule heating, not only that Joule heating play a big deal in terms of instability, the larger the Joule heating, and so that will trigger the instability. So not only the Joule heating play a big role in instability, but also the combustion heat release and other vibrational state and plasma chemistry, they all play an important role affecting instability. And then what about you do a detailed chemistry? Or you can do you can put that all detailed chemistry into it and say, I have omega ij, considering all different kind of elementary reactions. I can consider Joule heating, I consider that the energy increase in electrons, and then and so convective heat losses and chemical reaction heat release. You can put it into the equation, and you can model that plasma instability by using that the electric field and then the conductivity reactions relationship. And you can using a chemicane for combustion. You can using bosic for the electric field and the electron energy, and using hydrogen oxygen mechanism and the plasma mechanism to model this. So what you can see that you can also that using this computational singular perturbation that decompose the reaction into different mode. For example, you can, this is that the ordinary differential equations, and you can define the Jacobian of this source term as a function of your variables, and then analyze that the diagonal values of this matrix that's indicating your eigenvalues. So this F will be that is defined as the diagonal matrix multiplied by that by the F. So this is that the isolate and the decoupled eigenmode. This means that each eigenmode will grow with its own timescales of lambda I. So F will be projection of your source term and to source term to that each eigenmode. And you can see that if this lambda I is larger than 0, you are unstable. Is lambda I less than 0 is stable. So you can project that each about the mode, which mode is controlling that explosion or unstable. So by doing this, that you can analyze that the which reaction control that thermochemical mode, that TCMs, and which species are involved. To do that, you can do a numerical simulation with nitrogen oxygen, with the nitrogen, hydrogen with air, and with hydrogen air with different initial temperature. So you can see that at combustion, that the eigenmode, that the eigenvalue become positive at the ignition time. And in a plasma, nitrogen and oxygen without fuel, and you have that the eigenmode becomes positive due to that thermochemical instability. And if you have a fuel into it, you can see your eigenmode is going to be governed by that the coupling between plasma chemistry and the combustion chemistry, and the eigenmode becomes positive and grow very fast. If you look in the eigenmode, which one contributing at the plasma instability, you can do thermochemical mode analysis, just similar like a singular perturbation method by Professor Harvey Lam. You can see that the mode 1 is positive and lambda is positive, and which is the biggest one that drive with the hydrogen vibrational modes and generate a fast heating for the process. And also you can see that the second mode contribute to that the H and OH radicals and trigger that the combustion process. And the third mode, basically the excited species like N2A and N2B, they control that the atomic oxygen production. So by analyzing this positive eigenmode, you can see which are the important reactions in plasma and in combustion and in the vibrational mode, the governing your thermochemical instability. So this is that the advantage that the progress in combustion kinetic analysis can be used in plasma instability analysis as well. Now we can show you that it is a one-dimensional simulation. Before was like a zero-dimensional modeling. So now I try to show you that a one-dimensional modeling of plasma instability. So you have a 2 electrode, and which giving you that the electrical field, and you have a convection to cool down that plasma, and then we can see when this electrical field generated plasma is uniform and become contraction. So you can write down the governing equation in a cylindrical geometry, the electrons, negative and positive ions, temperature, vibrational states. And the charge conservation give you the relation between current and electrical field and conductivity. We use that reaction, this relation before. So if you have this solution, give you 2 possible results. One is that homogeneous. The other one is contraction. This is unstable. This will be stable. And we will see how combustion is going to affect that stability. So we're using that the hydrogen mechanism, which is HP Mac, using that the plasma chemistry and the vibrational excited species in the modeling. So we are running a different case. Initially, we're running just that like air. We're running nitrogen with hydrogen. We're running with a different hydrogen with oxygen and hydrogen at room temperature and at 800 Kelvin. This is a combustible mixture, at different temperatures. We'll see how that affects that plasma instability. So as you can see that if you look in the reaction, that the electron attachment of oxygen, and these reactions, if you perturb this reaction rate, let's say I increase this reaction rate, or I see how that affects the instability. So this basically is showing you that electric field as a function of current. So if you increase that the reaction rate, for example, from this is the water, this is the oxygen. So from by 10 times, you can see that the instability, this is that the red one, this is that the yellow one. So instability will be, if it's for higher one, it should be here. So instability will be extended. So that means that the plasma will be more stable at high current because of the high attachment. So what do you want to conclude from here? That the electron attachment to oxygen or electron attachment to water in the combustion product, they will stabilize the plasma and make it more uniform, all right? And also you can see that how does that the fuel ionization effect. If you're looking at that this is the nitrogen and oxygen, and then you have compare with the nitrogen and hydrogen. So one without fuel, the other one with fuel. So you can see with hydrogen that you can see the stability is much, much bigger. And without with oxygen, the stability will be very less. This is because that the electron impact dissociation of fuel and of fuel is endothermic process. And that can dramatically extend your stability of plasma. So what does this figure mean? The thing means that if you have plasma is unstable, and we can put a kind of a pyrolysis reactions into it, and that makes that the plasma more stable at a high current. This is important for chemical reforming process. So the next thing that you compare that a combustible mixture with a air, you can see that by considering that without combustion, with combustion. So without combustion, that the plasma is stable at 20, maybe 30 milliampere. And by considering combustion, the plasma is only stable at below 10 milliampere. So therefore, combustion, they dramatically narrow the limit of plasma instability. Again, this result is showing that one-dimensional simulation is showing that plasma chemical reactions is going to accelerate that plasma instability. And if you raise the temperature from room temperature, let's say 293 Kelvin, to a high temperature at 290 Kelvin, that basically the plasma trigger the ignition. At a higher temperature, that is ignition trigger the plasma. So we want to see these two different cases, the low and high temperature, how does the instability change? So in this case, you can see that the plasma is generating, this is that the radical production from that from the plasma, the OH formations. You can see the water formation by plasma. So in this case, that the plasma can basically trigger ignition and also that affect the instability. And the next case, we said the mixture, what if the mixture is very hot, 800 Kelvin? So all ignition will happening first. You know, this is that without the electrical field. And you can see that the electrical field equals 0. And you can see the all ignition coming first and before the plasma start. So the all ignition generate a lot of different species for the plasma discharge. So you can see here that so the electrical field at R equals 0 and R equal to maximum. So the ignition happening here and the plasma instability contraction is happening there. So from this figure, basically you can see that the electric field, this is the current, and you can see that with a combustion heat release, and you have a plasma instability and happening at contracted states. And so therefore, that although combustion can enhance that the instability, but that the mixture temperature also affects that the contracted states. So this instability happening at high temperature is different from that the state happening at a low temperature. So what I try to we try to conclude that by understanding that the plasma instability, we propose there is a new instability mechanism we call thermochemical instability, is coupling the plasma chemistry with a combustion chemistry. And the experiment with and the theory both show that the fuel air mixture is likely to become unstable in plasma discharge. And experiment and a theoretical criterion for plasma thermochemical instability is developed. And then the reaction pathways for key instability and then the responsible species can be identified using that the computational singular perturbation method or eigenvalue analysis. Understanding the plasma chemistry instability can help to control the plasma stability and to enhance that volumetric ignition and the volume, larger volume for fuel reforming. So I take a brief stop here if you have any questions.
Yes, we have two questions.
Okay.
First one from Tarish Tanija is asking about governing equations.
Yes.
On slide 17, I noticed that neutral species number density ODE is not solved. How is the system of ODEs is closed without it, since most of the excited states are neutral?
Neutral number density, because that in the plasma process, most of that for simple model, let's think about it. Your neutral number density is does not change much, because that the plasma is a weakly ionized plasma. Your electrons, your positive ions, and your negative ion concentration are at the ppm level, and your neutral number density actually does not change much. So that unless you are modeling a real combustion process in a simple stability analysis, you basically assume that the neutral number density does not change as a function of time. If you do a detailed numerical modeling, then of course, there's a nonlinear process. You have to consider that.
Another question from Tarish Tanija also. How does CSP with results from a 0D code help in arriving at conclusions about instabilities that are spatial in nature as per pictures of the experiments?
I think that the CSP, good question. First of all, that the CSPs only give you a local stability eigenvalue analysis. So in other words, the CSP give you the linear stability. And in our multidimensional discharge, that at every location, you can perform a linear stability analysis at every location to see whether you have a positive eigenvalue or negative eigenvalue at a single point. You can determine where that instability occurs at which location. And so in other words, you have to, for multidimensional systems, you have to perform that the CSP and as a function of time and space to understand where that the positive eigenvalues is happening and what are the active mode of that reaction kinetics.
Thank you, Professor. This is all the questions.
All right. So next, so let's continue and share screen. So in the next probably an hour, we try to discuss that the plasma modeling. So make sure that we will take a break in 30 minutes. So modeling plasma assisted combustion and chemical reforming is very critical. And particularly with that, the availability of faster computers and machine learning mechanisms, and you have great opportunities to model that the plasma, which was not possible probably 10 years ago. So in this seminar, we try to talk about three things. The first is that it is a plasma chemistry and how to model the chemistry. The second thing that we introduce you that is a multi-scale modeling using fluid model. And then we try to introduce in multi-scale modeling about that plasma catalysis and PowerPoint. So a plasma, I tried using a slide shared by Anime Bogarts. So what she says that plasma is a multi-scale process, and it's ranging from nanoscale all the way to centimeters. Just the scale is even smaller than combustion timescales, so you basically that have to understand normally that you understand the chemistry. So the chemistry you can think about it zero-dimensional, just like that the combustion chemistry is. And then you can start to do a macro scale modeling, including transport, including that the radiation coupling, including convection. So, and these will give you that the plasma dynamics in a volumetric or in a larger system. And this elementary reaction model that the reaction rate, it has to come from either experimental measurements and or the atomic scale modeling, particularly for plasma catalysis, and that the reaction on the surface reaction is so complicated. Even in the gas phase, you probably require on quantum chemistry computations, and on the plasma surface, you rely on either Monte Carlo simulations, or we could rely on that the density function theory model. So you can using this one as the input to optimize that the chemistry, and then you do that the large scale simulation, and then using that as a feedback to validate that the plasma chemistry, and also that in catalysis process, and that there is some kind of a catalyst is very small, and the catalyst bed, the pore is very small. So you need a micro scale modeling, probably including non-continuum mechanics. In there, you have to using either Boltzmann equations, or you can using that Monte Carlo or molecular dynamics, coupling with a DFT theories, modeling, and also use quantum chemistry. So this is that the a large multi-scale system. And what I'm going to talk to you today is showing you that the zero-dimensional plasma chemistry, and showing some example of two-dimensional modeling of macro scale modeling about this plasma combustion, and showing you some of that the micro scale in a Monte Carlo method done by Anime in terms of plasma catalysis. So first of all, in plasma chemistry, the most important part is that the electron impact reaction. So if you have electrons, you are impacted with a molecular, diatomic molecule, for example, you're going to generate excitation, generate a vibration, dissociation, excitation, and ionization, dissociation, ionization, and electron attachment. All these reactions, they are multi-channel, and you need to estimate the reaction rates. So in order to calculate reaction rate, and you need two things. One is that you need to know that the electron temperature, because all these reactions, they depend on electron temperature and the gas temperature. But also then you need to know that the cross sections of each chemical collisions. So therefore, to estimate that cross sections, And you need to know, calculate that if you have elastic collisions, and the reaction rate will be equal, that the collision rate will be equal to the cross-section areas, and also that with the distribution function as a different velocities. So for non-elastic collisions, and you need to have defined what is the threshold energy that the non-elastic collision process will occur, and what is that cross-section area or rate. You have to define it. I try to give you example that if you have electron impact, electronic excitation reaction, for example, and for example, you have electron impact with nitrogen, with oxygen, you have different kind of excited states. And then this excited states and require different electron energy or threshold energy to occur. For example, for singlet oxygen, you only need 1 eV or 1 eV to generate a singlet oxygen. For nitrogen A, B, C states is around here, and you need probably 6 or 12 electron EVs to excite this excited state of nitrogen. So therefore, you need a cross-section areas, which is that the excitation cross-section area, and to obtain the reaction coefficient. So these cross-section areas either measured by experiment or either computed by quantum chemistry. If you look in that LexCat database and in this internet, you can find that the cross-section areas for this kind of electron impact ionization reactions or excitation reaction database are there. So these are some of example about the cross-section areas. You can see the cross-section area itself is a function of electron energy. And so you need to solve two things: know your electron energy and know your cross-section areas. Once you know this, and you know that the reaction rate. And the other one is that electron impact dissociation reactions. This is very important for example, for oxygen dissociation to generate radicals, and also for methane dissociation to produce radicals and carbon. So this also you need to require a different threshold energy and then the cross-section areas. So this cross-section areas for methane and oxygen is also listed in that LexCat database. So you can find it. So next one is the electron impact ionization reactions. And for example, electron impact with oxygen and nitrogen, you can generate new electrons and positive ions. So these type of reactions, they have ionization threshold, and they also have the cross-section areas. By knowing this too, and you can calculate that the reaction rate for this type of reactions. And attachment reactions, and it's very important. They affect that the electron number density, and they also affect the plasma stability. So these cross-section areas, for example, electron attachment, O and O minus, or electron attachment to O2, and they are tabulated and in the database. You can use it to together with Bosic and to obtain the elementary reaction rate. The complicated part is that the reaction rate of vibrational excitation. For example, if you electron impact with nitrogen, they can vibrationally excite a nitrogen, and you can excite that methane, oxygen, and CO2. For methane, then you can say I have a different vibrational mode, symmetric stretching, twisting, asymmetric switching, and sistering. So these energies is generated are very small. It's by less than a half electron volts. All right. But if you're looking at a oxygen, is also that the vibrational excitation mode is less than 1 electron volt. So therefore, this methane and oxygen, a vibrational mode, can be excited as a very weak plasma field. However, for nitrogen, that the nitrogen excitation, and particularly at a high level, can require several electron volts. And this high energy can potentially trigger that the vibrational nitrogen can be chemically reactive, and is different from methane and oxygen. So for CO2, that there are three different kind of vibrational mode, and symmetric and asymmetric, and symmetric deformation. So bending. So this way you can see that the CO2 has can be excited with, for example, asymmetric mode with many excitation mode. They can reach electron energy levels to several EVs. So therefore, for CO2 and nitrogen, it's very important to consider that the vibration mode at high levels that has a very high energy, they can participate in the chemical reactions. And so the reaction involving vibrational excited state, they can have a vibrational excitation. They can also, that the vibrational state can relax to translational energy through collisions. The vibrational energy can be relaxed from high level to lower level, or can be excited from lower level to high level. And also they can trigger that the reactions, for example, the nitrogen and the CO2 at high vibrational states. So this needs to be properly modeled, and particularly for nitrogen and CO2 at high vibrational states. So the question is, what is the reaction rate in terms of vibration? So for example, if you have molecules and a reaction with vibrational excited molecules, and then they form a new product. So this reaction rate will have to be corrected from a Newton's law by using a vibrational energy, because as you can see here, the vibrational molecules, they are going to effectively reduce your activation energy, because their energy is stored in the vibrational mode. So this reduction is proportional to a coefficient alpha. The alpha is that the efficiency of vibrational energy to reduce that the energy barrier. So it was a model proposed by Alex Friedman and Drexel University and Matthew of Purdue. It's called alpha mode, introducing this alpha as the parameter. And this alpha is a function about that activation energy before the collision. You can see that EA1, this is the activation energy barrier before that the reaction. The RE2, it is that the energy barrier after the reaction. So that becomes that the ratio of these, the governing that how much alpha will be. All right. So that is approximate. And for diatomic molecules, for example, you have that the vibrational VT relaxations. So these VT relaxations can be modeled by using a new type of reaction model by introducing that the different constant with that energy difference about the VT relaxation. So for example, for nitrogen, hydrogen, and water, and CO2, and these parameters of M and N and ABC, they are tabulated here. But how accurate this is, and that is require experimental validation for these models. And for non-diatomic molecules, and people using a complicated model to fit this. There are several different models here, and they're involving a different kind of parameters. And these are the parameters of listed here. So you can use in this reaction to model this vibrational relaxation and in the kinetic model. And you're using a simulated result to validate it with the experiment. And you can see these days that with laser absorption spectroscopy or with that with cores, you can measure these cavity ring down. You can measure this vibrational states extremely well and can calibrate these models. So the really challenge that if you want to put this all chemistry into it, And this is a lot of challenges. You have a lot of is a multi-physics. You have photons, electrons, electronically excited, and vibrationally excited states, which typical combustion process doesn't have. And then you also have electromagnetic field, acoustic waves, shock waves due to the plasma generated and shock waves. And you have multi-scales and ranging from Debye length scale to reaction diffusion zone of flames, mixing layers, and electric field. Multi-time scale plasma is sub-nanosecond. Reactive flow probably is a microsecond to millisecond. And so it's very, very broad in time scales. And you're involving with stiffness. And if you say combustion is very stiff, the reaction rate is fast, but plasma is even faster. They'll make the reaction very stiff. And it's multidimensional, and some is a far non-equilibrium. So make your Maxwell distribution or Boltzmann distribution not valid anymore. So there are many, many challenges in plasma modeling, but it gives you a great opportunity to work on this because of this challenge. So there are different kind of a description about the plasma. You can use in Monte Carlo method or using a Boltzmann equations to solve the distribution functions and obtain the kinetic equation. So this basically can apply to the non-continuum regimes using kinetic model. And to simplify this for a larger system, this is probably limited to millimeters, very small length scales. You can use in the multi-fluid description just to solve that everything like fluid mechanics. So in this way, you only need to couple that the Navier equations with the plasma chemistry. So we'll discuss this and in terms of in the next 10 to 20 minutes. So a lot of plasma modeling tools has been developed. First of all, to model that electron energy distribution functions and using Boltzmann equations. So you can expand that if the plasma is quasi neutral, or if the plasma is the local, plasma properties is governed by the local plasma properties, and the electric field is not very strong. You can using that the first two terms expansion. That means the first order expansion about the distribution function. So V here is the velocity, Z is that electric field coordinate, and T is the time. And theta is actually that the angle between the velocity and the electric field directions. By using this two-term expansion, you can do three terms for more accurate, and you can solve that the electron energy distribution. So BOSIC is a solver that can be downloaded here, and you can use to model the electron energy distribution function by using BOSIC. And these days that BOSIC can give you that the electron energy distribution, and if you put cross-section area there about the reactions, they can also give you the reaction rate. And then recently that in Europe that they developed this ZD plus clean, and they couple this BOSIC with a VOD solver and with a database of cross-section areas with some kind of processors. They can give you an interface to model complex plasma chemistry. So if you can further couple it with chemicking, you can couple this ZD plus beam with chemicking to model plasma-assisted combustion. For example, that a few years ago, so in my laboratory, we coupled this ZD plus beam with chemicking. We basically using time splitting. We couple that the plasma chemistry with combustion chemistry by using time splitting. So therefore, we're using a ZD plus beam to handle that the plasma chemistry. We're using chemicking to handle the combustion chemistry. We couple them together using this time splitting method. This gives you a very flexible way to model plasma-assisted combustion. For example, if we model that this kind of hybrid plasma using this nanosecond plasma for electronic excitation, using dielectric current DC plasma to encourage vibrational excitation, or a low energy excitation. So we can understand how does a hybrid plasma can accelerate ignition process. I try to show you the results that you have this hybrid. You have nanosecond. Between this, you have a DC plasma discharge. The DC can be as a different kind of electric field strength from 1 tonsant to 5 tonsant to 10 tonsant. So as you can see from this figure, that you look at the electron number density, that electrons is generated by this nanosecond discharge here. And then depending on this DC electrical field, and you can see your electron number density is varied significantly due to your DC electrical field. And then if you model that the vibrational process, you can see as a lower electrical field, you generate a lot of methane vibrational modes. A high electrical mode, your vibrational mode is really very in the beginning of that a nanosecond plasma discharge. And you can also generate, for example, as that singular oxygen molecules and vibrational oxygen depend on what kind of electrical field you applied here. So you can promote, for example, that the singular oxygen generation with 10 tonsant. You can promote that the vibrational oxygen generation with 5 tonsant. So this gives you a selective control about that the plasma properties to control vibrational excitation and electronic excitation. As a result, you can see here that with this is that the vibrational excitation about the H plus O2 reactions with different kind of plasma field, and you can control this vibrational rate by changing that the different plasma field. You can also control the vibrational state reactions of methane with hydrogen reactions, and then the vibrational methane molecules with atomic oxygen, and vibrational methane with OH molecules. So by using this hybrid plasma, you can selectively excite that the vibrational oxygen and vibrational methane, so that you can control the plasma chemistry, and with the same energy deposit, and the ignition delay time will be different. There is a optimum DC electrical field with the same energy. They can accelerate the ignition process. So, and also that a one-dimensional plasma modeling using the fluid model was modeled, and I think probably this will work at the Georgia Tech, Yiguang's group, and using Poisson equation to model the electric field phi, and you can solve that the electron energy, electron number density, and and also that the K is a new number density of the case species, and then continuum equation, and then this energy equation, the viscous equation. So, and they're using Bosic to calculate the elementary reaction rate, and then they calculate that the number density as a function of time with a nanosecond discharge. You can see that the electronic excitation of nitrogen, and then atomic oxygen excitation, 1D and O1S at different time scales. And the problem, that one of the challenges is really that the lot of reactions, the computation is very complicated. If you difficult to model this with a ordinary differential equation solver, OD solver. So what we developed a few years ago using this kind of multi-time scale method. We look at the ignition in a combustion process, that at the different time of ignition event, the time scales of different species, they change a lot. You know, in the beginning, they're very short, and during the ignition process, the time scales become much, much shorter. So therefore, that the simulation of combustion is really limited by that the shorter time scales. The question is, how can we simulate this system and the computation efficiently without using ordinary differential equation solvers? And you can see that every species, and they have their own time scales. And even though they are coupled, you can decouple them by using their own time scales. By doing this, you can say that I am using for the faster species, I can using a small time scales. For the slow species, I can using large time scales. I can using model that the species in a few time step and give the data to the slow species. In this way, your computation time will be dramatically reduced. You can also using hybrid multi-time scale method. For the faster species, you can using an implicit solver. For the slow species, you can using explicit solver. You can couple them so that to increase the stability. If you have no interest in this kind of faster species in a small time scale. I try to compare with you that in combustion, we demonstrate that this ignition process or n-heptane, that this a multi-time scale method, they do extremely well in terms of temperature, species, and ignition delay time, and compared to the ODE solvers and everything else. So by computation, if you look at the computation time, this is a VOD solver, and if you are using for combustion and plasma, it takes you a lot of time. By using that the model reduction using adaptive chemistry, you can sort of reduce that the chemistry, but the increase that your time in terms of model reduction. And then by using multi-time scale method, you can see that you can dramatically reduce this computation time for chemistry, and then make them is comparable with the time of convection and diffusion. And by further using this correlated dynamic adaptive chemistry, and you can even make that the computation even faster. This is that. So the idea of this correlated dynamic adaptive chemistry is that you don't have to reduce that the model on the fly at every degree and every time step. You basically judge that if the key species is, for example, in the same phase space, for example, this 3 cells or this black cells, they are in the same phase space, and you just using the same reduced model to use it again. So by doing that, you say these cells, they are correlated and in dynamic adaptive chemistry. By doing that, and you can see that this is the ODE solver, and this is the H multi-time scale method. And by using this correlated and dynamic adaptive chemistry, Kodak T, you can see that the chemistry time and it's much shorter, and compared to the VOD, and it becomes almost the same or even shorter than your convection and diffusion, making it much more efficient to model that the flame propagation and the ignition process. So next, I try to. Okay, so let's take a break again. Take a 10 minutes break and to 4:40. Let's come back. Any question here?
Yes, we have 2 questions.
Okay.
3 now. First question from Kiang Ching. What is the main challenge of using plasma in highly turbulent conditions? Is it possible to couple the plasma model into LES?
I think that for LES, you are doing time accurate modeling, and the answer is yes. The challenge is that the time scales are different. In LES, you probably only care things about microseconds, and but in plasma, most of the things happening probably in 100 nanoseconds, and you have so you need to couple that 2 different time scales and into the modeling.
Another question from Anurag Surapani. The splitting between plasma and chemical scales, is this similar to the strand splitting technique used in some combustion codes? And does the order of splitting, first or higher, introduce error?
So if the timescales, they are significantly separated by 2 orders of magnitude, the error will be very small. But sometime for example, if the timescale, they are coupled with the same, in a similar, less than 1 order of magnitude. So therefore, that the error will be increasing. And if you try to split them. So probably you have to find that the gap between 2 reaction groups, they have a large timescale difference in order to reduce the uncertainty. Otherwise, you can use a implicit method to reduce the uncertainty. And it's different from the strand splitting. And this is a strand splitting is more like a species splitting, and this is more like a timescale splitting, and is not from a strand splitting using a matrix. It's not. It's basically the timescales between different species.
Another question from Anarita Vigiano. Are there experimental measurements in spark ignition engines where the intake air is partially ozonized?
I think that there's a lot of experimental measurement in spark ignition, but the data is really not quantitative. They probably only take a TALIF of OH at some kind of shot. It's not even time accurate, and so that makes it very hard for combustion. Plasma assisted combustion to be validated with the experimental data. But I think that with that the laser diagnostic capability I just presented to you yesterday and today, I think that you can see in the next few years, I would say that there will be a quantitative measurement about that in a combustion environment, about that the plasma properties and combustion properties in ignition process, and then they will be able to be validated against the simulation.
Last question. What are your thoughts on plasma-assisted combustion in IC engines? What would be the most ideal configuration to get uniform discharges at elevated temperatures and pressures as in an engine environment?
That's an excellent question. And right now, that most of that in the engine, people using spark or using multi-spark. And there are 2 new type of ignition right now is happening. People using this kind of cascading ignition. That means that the ignition start along a line, and you ignite it one by one, so that you generate a multiple spark in the line. That can increase the ignition volume and overcome the critical radius of ignition. The other one, that's like what Toyota is doing, that they try to increase the ignition energy so that they form a gliding arc as a strong turbulence to drive the arc to elongate to a long arc, so that you can ignite a larger volume at the lean burn conditions. And the third way that people are try to using this kind of radio frequency and this kind of streamer discharge or corona discharge using multiple fingers that generate these corona in a larger volume. But the corona, sometimes that the temperature is lower, they can trigger a larger volume ionization, but it may not be good to ignite the mixture for lean conditions. So therefore, probably corona, multi-finger corona discharge probably is good for HCCI type of ignition control, but may not be very effective for very lean burn combustion.
Thank you, Professor. This is all the questions for now.
All right. So okay. So let's back about 4 minutes, and so let me grab a.
You can start.
All right. So so we'll come back, and I guess a lot of people get very tired right now. So the next thing we try to show you that the multidimensional modeling using fluid model for plasma discharge and plasma assisted combustion. So here that is a simulation by a plasma physics group, and try to model that the plasma discharge between two electrodes, and try to compare with experiment and using a nanosecond discharge. And to solve that the species equations, and this is that the mobility and diffusion, and this is that the Poisson equations, and to try to solve these coupled system and in a plasma discharge and using fluid models. Again, my PowerPoint is freeze. Sorry. So let me stop it. So sorry for that. So you can see that this plasma discharge, and between these two electrodes can be modeled by this two fluid model. Hiding this. So this is that the simulation result. You can see that this is a cathode, this is the anode. So you can see initially, you can see the electric field, and it's a kilovolt per centimeters is developed at the initially at the anode. So you can see that at the cathode, well, that the electrons and will be emitted from the cathode. They propagate very fast and generate a very high ionization waves and from the cathode. At a certain point, at 4.3 nanoseconds, and you can see that this cathode ionization waves and then anode waves, they merge together to generate a discharge, arc discharge. So this dynamics can be modeled and fairly time accurately, but with a very short time scale, a few nanoseconds. But you can understand a good chemistry, what is happening in terms of time scales. So you can see at the very short time scales and below a few nanoseconds, you can see that the temperature is rising, and because of the fast heating, you can see that the oxygen, atomic oxygen is generated here, very high concentrations. And you can also see that the OH concentration is high. And then you can see the electron number density is rising very fast and the decay very quickly after that the discharge. So in terms of the gas heating, and she conducted that the analysis of different reaction rate, seeing that this excited nitrogen with oxygen, they generate a atomic oxygen and give that the extra heat, and with a 281 Kelvin increase. Another one is the N2C state with oxygen, it dissociated with atomic oxygen, and they give you additional more energy and for gas heating. And then this dissociation of hydrogen also generated gas heating as well. As we discussed before, the fast heating, mostly that are proportional to the oxygen concentrations due to N2 excited state with oxygen and O1D generation with the fuel as well. So therefore, this is a two fluid model, and they can give you that a quantitative time accurate predictions about this ionization process, the radical production process, but cannot give you a time scale that a combustion plasma assisted combustion needed. So there is a software developed by Yifei Joule and his collaborator in France and in China, and they call PASCI. They call parallel streamer solver with kinetics. So this basically includes that a mesh generation, a Poisson equation, a metric solvers, and with a photoionization and the plasma kinetics model, and to develop this for plasma discharge. And this is validation of PASCI and by Yifei Joule and in 2017. So this is that the volumetric streamer discharge at a different time, the different location. And they also validated this model at PASCI with experiment. This is the ionic wind. It basically has a discharge, dielectric barrier discharge, and you form that the current as a function of time for comparison. So this PASCI has been recently validated in a spark ignition, not ignition, in a spark discharge, and this kind of dielectric barrier discharge, and provide a great platform to integrate that the combustion modeling with it. So recently that I have a postdoc at Dr. Xinqian Mao is try to integrate that the PASCI with that the a solver, that adaptive simulation of unsteady reactive flow solver that is ASURF plus, and together with a multi-timescale method. Try to couple the PASCI in terms of plasma modeling and using the ASURF and multi-timescale method for the combustion and plasma modeling. So, and this basically show you an example that recently we did that the simulation of plasma ignition. So here the electrode, and with the anode, with the cathode, the separation distance probably is about 2 millimeters. And we studied how that the voltage shape and the time and the electrode geometry with parabolic, with a spherical head, with a different distance is going to affect that the ignition. So try to show you one of the results is showing that the simulated electrical field and electron temperature and electron number density, you can see that the electrons is emitted from that the cathode, and then they propagate towards that the anode and form some kind of arc discharge at the edge of the electrode. So you can see that the geometry play a very important role about that the ignition process. They are not uniform between the gap at all. And this modeling can provide you that the active species production, like O singular delta between these two electrodes, and oxygen and temperature evolution and the ignition process. And you can use in this software to optimize what is that optimized electrode, what is that the suppression distance, and they give you that the faster ignition with the same ignition energy. So the result basically showing you that what are the active species in terms of vibrational states, fast heating, and excited oxygen production and radicals, and in the plasma process, as well as the ignition process. And this also show you that the ions and the excited state of nitrogen produced in the process. So this kind of a multidimensional modeling by integrating PASCI with adaptive simulation of combustion model that give you a capability to conduct that the two-dimensional or even three-dimensional modeling about the plasma discharge, and give you a tool to optimize that ignition process. And the next thing we try to show you the recent modeling by Professor Bogus, and so model that the plasma catalysis and in a packed bed. So normally that if we want to do a CO2 reduction, and you have a dielectric ceramic particles on the surface of particles, you load catalyst, and you flow with CO2, maybe with methane or maybe without methane, and you fire the plasma DVD discharge in this channel, and you try to making the CO and oxygen from CO2. And the energy efficiency here is that only a few percent, of course, but that if you can find that the plasma, a good plasma catalyst, maybe and control that the excitation about the plasma itself, hopefully you can increase that the efficiency of CO2 reduction and to syngas. So what she did is she basically using the fluid model to simulate that the pack, and you can have that this is one particle, the other particle, you can see the electrical field and it become very strong, and at the very sharp tip of that the particle bed. And so you can also see the electron temperature at the high electrical field. Electron temperature is also strong, and you can see the correlation between electric field and electron temperature. And if you have a different, another, for example, particles there, and this gap distance will suddenly generate that the discharge. You can see a very strong electrical field and is formed here, and the electron temperature is also high. And so what they say is that the fluid model can give you a predictive modeling about that the electrical field, electron temperature, and then with different geometry in a small system. And in order to model that, how does streamer propagation in this kind of a plasma catalyst bed? What she did model this. You can see that at the different time, and you can see how that the plasma developed. And from here, you can see that there's a gas phase discharge propagation, and also there's a surface discharge. And you see that discharge gliding on the surface much faster than the gas phase discharge. And then so they form the discharge at the entire field at probably around 12 nanoseconds. So again, so this type of simulation, they can give you that the filamentary micro discharge and surface ionization wave modeling, and but there's very few experimental data available to validate this type of models. So and then to model micro discharge and with a non-continuum media. And what she did, she using a particle in cell, it's a Monte Carlo method to model that the streamer at three-dimensional fluid dynamic structures within honeycomb. So as you can see that using that the honeycomb structures, this one is the parallel channels. You have one channel, two channels, three channel parallel channel. You try to see that how that the electrical field is developed in this kind of a parallel channel. And she also using that the electric field from the parallel channel in vertical direction, and how that the electron number density and is developed from a one electrode to the second electrode. And also you can modify that these parallel channel into a 3D structures, and your 3D fluid dynamic structures. You can see that how that the discharge is formed from upstream to downstream. So what I try to say is that today that there's a lot of different kind of simulation tools has been developed using Bosic or model, or using a chemicking and integration with Bosic, or using Pascal with adaptive combustion simulation solvers, or using this kind of particle in cell and Monte Carlo method, and to model the various plasma discharge at the different length scales. And there's no best reaction model, but just that it's multi-viscous, multi-scale problem. So the key things, as she said, that we need that the experimental validations. A lot of simulations today. There's many parameters are artificial, and there are many models applied, but very few in situ laser diagnostics today is available for this kind of detailed and time resolved, spatially resolved measurements. So with that, I try to end my talk about the plasma modeling. Then I continue to share some. Okay, this is share my screen that you can see. So this will be that is the last two slides I want to discuss with you about that. What is that the future? And if you have any question, we can wait to the toward the end of this discussion. So we presented you about that big picture about that the plasma assisted combustion and the chemical conversion. We presented you that the applications of plasma assisted combustion and the fundamental research of plasma assisted combustion, and also that the plasma diagnostics, plasma simulations, and plasma instability. And then what is the future research of plasma assisted reactive flow? I won't call combustion, but I think that I will call a reactive flow, which include both combustion and chemical reforming. And so if we are thinking about plasma combustion, really that there's a lot of study has been done in terms of what is that the impact of plasma on combustion catalysis. That is that the most of the result, probably 90% of the result, and is one way, plasma to combustion, plasma to catalyst. But the really is important that as I show the plasma chemical instability, it is that combustion can have a strong feedback to plasma. It is how does combustion affect the plasma in plasma assisted combustion or chemical reforming is very, very rarely studied. And another, the same thing is how does the catalyst is going to be affected plasma. For example, can I design a different catalyst shape or chemical composition or different materials that are going to not only change that the yield of chemical reforming, but also change the plasma property itself. That is also poorly understood. So what are the traits that there are a lot of forward reactions, but studies, but very few backward and studies. I think this is the most important part in terms of plasma science. If you want to study plasma, you should propose in this way a backward, not to the forward. And the forward, you propose to combustion society, you propose to catalyst society. But I think that the community right now is coming together. Plasma assisted combustion people, like many people in the room, and then plasma catalysis, like enemy, and plasma physics people, and they all right now come together. And the DOE, as I said, found a plasma science center. They put people in plasma combustion, plasma catalysis, and plasma physics together, and to discuss what is that the findings, what is the next step to go. And they funded two centers, plasma science centers and plasma facility centers at Princeton and then at the San Diego National Lab. I think that it will be exciting 5 years from in the next 5 years to see how that the integration of different society that it can generate a new thinking and new ideas and a new approach in terms of modeling and experiment. So in terms of future research about that, the plasma research, in general, what are the game changers? And in terms of non-equilibrium plasma, from my personal perspective, what I try to say is that first of all, and the advanced engines, for example, very lean burn, equivalence ratio is less than 0.3, for example, and plasma assisted HCCI engines, and gas turbine engines, for example, using ammonia and hydrogen, very lean conditions, and relight problems of an ignition ammonia combustion. So this is going to be a very interesting that to see how non-equilibrium plasma that can help to extend that extreme combustions to lower carbon and to ignition. And in terms of chemical synthesis, then really that is the important thing is how do we control that the plasma properties to increase that the selectivity and yield, and how do we develop a novel plasma catalysis that takes advantage of non-equilibrium excitation and surface discharge and electric field, that in new catalysis, non-equilibrium catalysis, that enabling that the CO2 capture and utilization, as well as that hydrogen, ammonia, and chemical synthesis. This is really something big in the future, in my opinion. And then the question that can we using a plasma to generate materials? A lot of people making materials using combustion, using whatever, but plasma can enabling that synthesis in a non-oxygen environment and even in a nitrogen environment, and can make a new type of non-equilibrium catalysis that typically combustion and other CVD methods cannot do it. So this will be a very interesting and studies. A lot of people in the plasma field, they're looking at that the biomedicine can, of course, plasma can kill bacteria, can plasma and kill, cure cancers, can plasma can do, kill COVID-19 viruses. And there's a lot of interest in this area to understand what is the discharge at the interface between liquid and gas, and what are the chemistry that they kill bacteria and causing, and kill viruses. So this is an interesting area as well. Electronics, and today that people are making chips at 3 nanometers. In the future, probably have to make it in 1 nanometer, 2 nanometers. And how do you effectively that the fabricate that a structure, that electronic structure, close to or below this debye length, and what is that plasma transfer in that kind of a length scales. So there are many things else. Water purifications. There are some kind of other, environmental NOx reduction, many other things. So I put it the dot sign here. So the many game changers in the future, particularly with renewable electricity, enabling that the non-equilibrium plasma to be a big player and game changers. In terms of plasma control, is really that how do we enable the plasma stability at high pressure and without developing this kind of arcing, right? How do you increase that the selective excitation using hybrid plasma, for example? You can generate a electronic and vibrational excitation as the location and time I want. And how do you increase that the selective active species and radical production to promote chemical synthesis and combustion? How do you reduce the cost and the electronic noise about the plasma resources, and many others. So these are the game changers in plasma control. And to enabling 1 and 2, the important things is the fundamentals of plasma chemical synthesis, plasma aided chemical synthesis, PSC, plasma combustion, or plasma chemical synthesis. Really, that one thing is that the diagnostics in situ of electric field, number density, excited states, and the chemical non-equilibrium. Today, that is the all different kinds of mid-infrared, femtosecond lasers, and give you a tremendous opportunity to understand that the time-dependent plasma physics and chemistry. In terms of plasma physics, is that what is that energy, non-equilibrium energy transfer from electrons to excited states, from excited states to that the neutral molecules, and how does that affect the plasma chemistry and the instability and dynamics? So in terms of plasma chemistry, it's really that quantitative understanding of excited states and energy transfer efficiency. What is the non-equilibrium kinetics, and how does the plasma chemistry, particularly on the interface between gas phase and then catalyst, and between gas phase and the liquid. So these are the very interesting things. And kinetic modeling models that is poorly developed, poorly validated. Only a few are really validated in the lab. So we are trying to develop this plasma-associated ammonia combustion, and hopefully we will have a paper to the symposium. You will see and next year. And so the key species measurement, reaction rate, and cross-section area measurement is the key to develop quantitative plasma models together with quantum chemistry. And can the quantum chemistry expert come to this area and to enabling the capability of theoretical chemistry for plasma-associated combustion and chemical conversion. I see this is a great opportunity. And then the multi-scale modeling, connecting from atomic scale to macro scale. So these are the grand challenges in terms of predictive modeling in the future. So maybe there's some more and I may miss it, and I'm willing to hear from you and discuss with you. And the next slide, and I try to share with you, that is not my slide, is actually the slide from Anime Burgers. She is expert in the area of computational modeling and experiment of plasma catalysis. I asked her to share with me, from your perspective, what will be the very important questions for plasma catalysis. And she gave me this slide. And she says that how does that catalysis affect the plasma? So that's exactly the question I was asking. The backward is that catalysis affects plasma, not just plasma affects the catalysis. So what is the electrical field enhancement? How does plasma catalysis affect that local electrical field enhancement? What is that the change of discharge type from surface discharge to streamers and to arc to glow discharge? So due to the change of catalysis or structure of catalysis, can plasma penetrate that the catalyst pore? The catalyst is supported by particles, ceramic particles, and they have a lot of pores. What is the role of the pore affecting the plasma properties on the surface? Can plasma penetrate or diffuse into it? So what is the new products formed at catalytic surface if you have a different plasma electrical field? And is there any new reaction pathways, any new species generated? How does that the surface absorption of molecules to the surface is going to be affected by charge, by electric field? And you see, this is that the question, everything. If absorption on catalyst, how does that affected by plasma and then the charge, surface charge? So this is the question she was asking, and I completely agree with this. And then the question, how does plasma affect the catalyst? And she said, oh, in active radicals, excited species, and how do they interact with catalyst, right? So laser diagnostics will give a tremendous powerful tool to understand this. And then effects of electric field on surface reactions. Well, this is not really understand. I think that the DFT and the quantum chemistry simulation, hopefully even reactive molecular dynamics simulation probably give you some answers on that. So the electric field, how does the electric field affect the surface reaction? Because the electric field can change the polarization of your molecules. Will that polarization change that the reaction rate on surface? At least change your absorption coefficient probably, and maybe, and change your spin forbidden reaction could be, and if you have magnetic field, and also. And how does the surface morphology on behaviors of species on the surface? Well, that the surface morphology basically changed that the plasma discharge, and they are going to change that species of the surface, and they are changed that the plasma, diffusion and properties. So these are the questions from the world expert in terms of plasma catalysis. So I just want to share this 2 slides with you, and one from myself working on plasma combustion and plasma chemistry, chemical conversion in gas phase. And the other one is from Anime Bogas, who is an expert in plasma catalysis. So we try to combine that, share you my vision and her vision, and in terms of what is the future of plasma research in these areas. And with that, and I try to conclude that the future, that the plasma modeling and the experiment multi-scale has a grand challenge and has a long-term perspective. So we are going to organize an international workshop in 2023 in Germany to discuss that to probably assemble 80 participants, and to discuss what is that the opportunities, challenges, and of plasma chemistry and catalysis, and how do we collaborate internationally. So we will have an announcement probably by the end of this year, and hope some of you will join us in Germany in spring of 2023. All right. So with that, I thank you for your attention for 3 days, and it's a tremendous effort. And for me to speak for 9 hours is more effort from your side, and to listen for 9 hours. I really appreciate that. I hope that one day we can meet in person, and you can tell me, hey, Professor Joule, I have a great idea to do that. I would be very happy to hear that. And when we have an opportunity to meet in person. Thank you. With that, I try to take some questions from you, and hope that you enjoyed your combustion summer school online. Thank you very much.
Thank you, Professor, for the interesting talks.
So you can bring, if people ask a question, you can bring them into this webinar so that we can see, and at least on the screen, so I know who she or he is. Right. Any questions?
Okay, till now there is no one posted yet.
Okay. Oh, wonderful. So that means my talk either is terrible or is perfect, and no question come out. All right. Okay. With that, I think people probably get exhausted. And it's 3 hours, and this is a very complicated phenomenon. They get very tired. So, but well, to me, this is a very exciting area, and so a lot of opportunities. I see that one question is in the QA.
Yeah.
Thank you very much, Professor Joule. Was interesting and useful. All right. Thank you, Tawfiq, and I look forward to see you in the future. All right. Is that okay with everybody? All right. Thank you, everybody. And, and have a great enjoy your 2 more days of Princeton Summer School, and look forward to meeting you in the future. Stay healthy, stay hungry. Thank you very much.
Thank you, Professor.